These are examples for Lesson 8.2, Symmetry, Dilations, and Compositions. In this video, you'll learn to perform dilations and combinations of 2 or 3 transformations called compositions. You'll also learn to determine scale factors and also to determine point and line symmetries of various geometric figures. Example 1. The vertices of triangle ABC are at A 3,2, B 6,3, and C 7,1. Find the coordinates of the image of triangle ABC after a glide reflection using the composition of 2 transformation rules of translation followed by reflection. And so we start with the triangle's vertices, A, B, and C. A at 3,2, B at 6,3, and C at 7,1. Graph those points and draw the triangle. A is at 3,2, B is at 6,3, and C is at 7,1. In a glide reflection, that particular composition is always a translation followed by a reflection. Now that we have that triangle, we can perform the first transformation, which is a translation with this rule, xy, such that x minus 12y. So we transform A to A prime. We take x, which is 3, and subtract 12, according to the rule, comma, y, 2. That gives us A prime at 3 minus 12 is negative 9, comma, 2. Then we graph, or we find the transformed or translated B prime using the same rule, 6 minus 12, comma, y, which is 3. So B prime then is at negative 6, 3. And C prime, using the same rule, 7 minus 12, comma, 1. That gives us C prime at 7 minus 12, or negative 5, comma, 1. Now we take these ordered pairs and graph them in our first step in the composition. Starting at the origin, negative 9, 2 for A prime. 1, 2, 3, 4, 5, 6, 7, 8, 9 up 2. So there's A prime. It's been translated all the way over this way horizontally. Start at the origin for B prime, negative 6, 3. 1, 2, 3, 4, 5, 6 up 3. 1, 2, 3. There's B prime. C prime, negative 5, 1 to the left 5. 1, 2, 3, 4, 5, and then up 1. There's C prime. Take your straight edge, draw that resulting triangle. This is the intermediate triangle before the final image. And there's been a slide. Translation. Then we perform the second one, the reflection. And remember, the reflection rule for over the x-axis is xy, such that there's a reflection over the x-coordinate where x stays the same and y is multiplied by negative 1 or is negated. So a double prime, because we've moved it twice, is going to be applying this rule, the x-coordinate negative 9, comma, negative 1 times the y-coordinate 2. And that gives us A double prime at negative 9, negative 2. And then for B double prime, applying the same reflection rule, we get negative 6 and then negative 1 times 3. That gives us B prime, double prime at negative 6, negative 3. And finally C double prime, applying the reflection rule, we get negative 5, comma, and then negative 1 times y, which is 1. That gives us C double prime at negative 5, negative 1. Now we take these and graph them. Starting at the origin for A double prime, negative 9, negative 2. to the left 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 down 2. 1, 2. There's A double prime. Starting at the origin, -6, -3. Go to the left 6. 1, 2, 3, 4, 5, 6. And down 1, 2, 3. There's B double prime. C double prime is -5, -1. So we go to the left 5, down 1. There's C double prime. Connect the vertices for your final image triangle. And remember, the glide reflection is always a slide and a flip. A slide and a flip. Horizontal slide and a flip. And there's your resulting image. Example 2. Draw all the lines of symmetry and determine the number of lines of symmetry that each hexagon has. For lines of symmetry, we're talking about reflective symmetry. And as discussed earlier in the lesson, if you can fold that figure on itself and one half of the fold matches the other half, then you have a line of symmetry. So in this first one, A, if we were to fold right along this vertical line from the center and folded this part over here, this line being the fold, it would match. Each point would match here, here, and here. We also could fold a horizontal line, and if we folded this upward this way, these 2 points would correspond and match these 2 points here, and everything would trace itself. So there are no other lines of symmetry here, no matter which direction we go. If we were to fold, for instance, along this diagonal right here that I have, this point would come somewhere over here. This point would come somewhere over here, so it wouldn't trace itself. There's no other possible way. So this one, yes, it has line symmetry. It has 2 lines of symmetry, but it does have line symmetry. This next hexagon is what is a regular hexagon, where all the sides and angles are congruent. And so performing the same type of thinking, or applying the same kind of thinking, we try to fold it along a line and see if it'll trace itself, and it does. If we draw a line right down the middle vertically, we have this side over here will trace this side over here. So in a real similar way, if we draw a line through this particular position here and fold this image across this line, these 3 points will match with these 3 points here. And once again, if we draw a line in this direction, this side of the figure here, these points 1, 2, and 3 here will match with these 3 over here. Now that's 3 lines of symmetry, but there are more. If we were to fold right along the vertices of this figure, then this part over here would match or correspond this part over here. So this is also a line of symmetry, line symmetry number 4. And if we do something similar with all the other pairs of vertices, we've got another line of symmetry here, where this part flips over to this one. And finally, one more through these 2 vertices. Be careful when you're counting these up. This is 1 line of symmetry, 2, 3, 4, 5, 6. Be careful, this is not line 7, this is line 1. All these are already counted, so there are 6 lines of symmetry. Finally, in this last hexagon, we try to fold this, and we look and see if it'll trace itself anywhere we create a fold line. And the only place we can create one is horizontally, right here. If we fold it right on this line, this part of the figure will match this part of the figure, and that's the only line possible. So one line of symmetry. Now you practice too. For example 3, it asks, does each figure have rotational symmetry? If so, describe any rotations that map the figure onto itself. A key in trying to determine rotational symmetry is the point of symmetry and a tracing. But you have to be careful because it involves rotating and not folding this time. I have a similar or almost congruent rectangle that I'm placing over this one. I'm going to trace it. And I've got this guideline right here, guide segment. And what you do is you put your pencil right on the middle of that figure, right in the center point where the rotational point is. And you start turning your tracing counterclockwise. And you do this until the figure matches itself. Not the guideline, but the figure itself. Once it matches, then you have rotational symmetry, but it can't be more than 180 degrees. So this has matched itself for the first time. So I'm going to make a little mark here, and I'll draw a little straight line segment here back to the point of symmetry. This was 180 degrees. So this does have rotational symmetry, yes, and it's 180 degrees only. There's only one angle of rotational symmetry here. Since it's 180 degrees or less, it does have rotational symmetry. So we say that therefore, this figure has 180 degree rotational symmetry. Or we can say it's got point symmetry. For the next one, I take a tracing of the regular hexagon, and I do the same thing. I put my pencil in the middle on that point of symmetry, and I start turning it counterclockwise until the figure matches itself. Right there, it matches itself. So this guideline right here, I'm going to go ahead and draw back to the point in the center. This angle right here is an angle of rotational symmetry. Let's keep going and see if we can find some more. Start where you left off, continue to rotate counterclockwise until it traces itself once again, and there it is. It traces itself right here. And so this angle right here is an angle of rotation for this figure. And we haven't gotten to 180 yet, so we continue. And we continue rotating counterclockwise until the figure traces itself, and it traces itself right at 180 degrees. So it's also got rotational symmetry at this amount of degrees. This is 180 degrees because it's completely the other direction. So yes, it has rotational symmetry, and it's got this degree, and this degree. So how do we figure that out? Well, one way you can do it is you can take 180 degrees and divide by how many times it retraced itself. So we could find it by saying 180 degrees divided by 3 tracings is equal to 60 degrees. So it's got 60 degree, 60 plus 60 is 120 degree, that's this one right here. And 60 plus 60 plus 60 is 180 degrees. These are all the degrees of point symmetry that it has. Now, this figure, though, has 60 degree point symmetry. you always use the first tracing that it had and use those degrees for the point symmetry. So this is regular hexagon, has 60-degree point symmetry. And our final one is a kite. We've got a tracing of it. And doing the same thing, putting my pencil at the point in the center. I start moving my figure counterclockwise until it traces itself, or until 180 degrees is reached. Now we've reached 180 degrees now, and it never has traced itself. So this figure does not have rotational symmetry. So no, there is no point symmetry. Example 4. Draw a dilation of quadrilateral ABCD with vertices at A 2, 1, B 4, 1, C 4, -1, and D 1, -1. Use a scale factor of 2 and label the image FGHJ. Okay, so to start off, we have our scale factor is 2. That means K is equal to 2. We use K. And since 2, or K, is greater than 1, then this is an enlargement. So, the rule for dilations, whether enlargement or reduction, is XY, such that there's a dilation, KX, KY. So K always multiplies with the X and Y coordinates. Since K is 2, we use 2 here and here. So we take the ordered pairs A, B, C, and D. We graph them. Get them on here first. And graphing the original figure, 2, 1 is A. 4, 1 is B. 4, -1 is C, and 1, -1 is D. Take your straight edge and draw this quadrilateral. This happens to be a trapezoid because one pair of opposite sides are parallel, and in particular it is a right trapezoid because it has 2 right angles. Okay, so performing our dilation, we have A prime, where K is 2. So I have 2 times the X coordinate, 2, comma 2 times the Y coordinate, 1. And that gives me A prime at 4, 2. For B prime, doing the same, using the same scale factor, we have K, which is 2 times 4, comma K, 2 times 1, the X and Y coordinates. It gives us B prime at 8, 2. And then C prime, we use K is 2 times 4, comma 2 times -1. That gives us C prime at 8, -2. And finally D prime, using K equal 2, we have 2 times 1, the X coordinate, comma 2 times -1, the Y coordinate. And we get D prime is at 2, -2. Now we take these and graph it. Starting with A prime, we have 4, 2. 1, 2, 3, 4, up 2. So now A, instead of being here, is over here, A prime. B is at 8, 2. 1, 2, 3, 4, 5, 6, 7, 8, up 2, 1, 2. So here's B prime from its old location. And then C prime is at 8, -2. 1, 2, 3, 4, 5, 6, 7, 8, down 2. There's C prime. And D prime is at 2, -2. To the right 2, down 2. And there's D prime. Take a straight edge and connect all 4 vertices. We discussed that this should be an enlargement, and as you can see, it is going to be an enlargement. And it happens to be twice as large as the pre-image or original. One more thing we need to look at. When you do a dilation, at least in this class, when you get to pre-calculus, we'll do some some heavier work. Your point of dilation will always be at the center of the origin of the coordinate plane when you're on the coordinate system. So we'll call this O for origin. Notice how if you draw a line segment or line through the point, the origin point, the point of dilation, it goes through both the image and pre-image points on every single vertex for A and A prime, for B and B prime, for C and C prime, and for D and D prime. This will always be true as long as you're, well, this will always be true from the point of dilation when you perform a dilation. Notice that OA is half the length of OA prime. Also notice that OA, the length of it is equal to the length of AA prime. And you can make a whole bunch of statements based on this. Example 5. A triangle has vertices at A 4, -4, B 8, 1, and C 7, -4. Find the new vertices of the image triangle A prime, B prime, C prime after a dilation of triangle ABC with a scale factor of K equal 1/2. This time we have a dilation where K is 1/2, less than 1 and greater than 0. So because of that, we have a what? A reduction. So again, we take our ordered pairs, A, B, and C. A is at 4, -4. B is at 8, 1. C is at 7, -4. We're going to dilate to find A prime. Let's go ahead and graph these on our coordinate system first. We have A at 4, -4. 1, 2, 3, 4, down 4. 1, 2, 3, 4. B is at 8, 8, 1. 1, 2, 3, 4, 5, 6, 7, 8, up 1. So there's A, there's B. C is at 7, -4. 1, 2, 3, 4, 5, 6, 7, down 4. 1, 2, 3, 4. There's C. Take a straight edge, connect the vertices, and you have yourself a slight obtuse triangle here. Obtuse angle C there. Okay, performing the dilation, we use K as 1/2. Remember, K is multiplied with both vertices, so we have 1/2, or K, times the x-coordinate 4, comma, 1/2 K, times -4. So A prime is 1/2 of 4, or if you want to do it this way, put 4 over 1. 2 and 4 divisible by 2. 2 goes into 2 once, 2 goes into 4 twice. You get 1 times 2 over 1 times 1, which is 2 over 1, or just 2. Or just simply say 1/2 of 4 is 2. 1/2 of -4 is -2. To dilate B, for a reduction, do the same thing. 1/2 is K, multiply it with 8, comma, 1/2 times the y-coordinate, 1. That gives us B prime at half of 8 is 4, half of 1 is 1/2. Half of 1 is 1/2. And then to dilate C, C prime, we get 1/2 times 7, comma, 1/2 times -4. That gives us C prime at 1/2 of 7 is simply 7/2. If you want to write 3 and 1/2, that's fine. Comma, 1/2 of -4 is -2. Now we're going to take these and graph them. Starting with A prime at 2, -2. Go to the right 2, down 2. There's A prime. So A has moved back away from this origin, this location, back to this location closer to that point. So there's A prime. And then B prime is at 4, 1/2. So we go to the right 4. 1, 2, 3, 4. Up 1/2, 1 out of 2 in a full unit. That would be right here. So there's B prime. And then C prime is 7/2, -2. Well, 7/2 means I take each full unit, cut it up into 2 equal parts, and go 7 of them. To the right, 1/2, 2/2, 3/2, 4/2, 5/2, 6/2, 7/2, and then down 2 full units. 1, 2. So there's C prime. Take my straight edge and connect the vertices. And you'll notice that this new image is half the size of the pre-image. And once again, I won't do all of them, but from the origin, the point of dilation is the origin. The original and image points line up. Example 6. Now, compositions can be done in a certain order like we did earlier, or they can be done all at one time. Here's one that demonstrates how a composition can be done all in one rule. Find the coordinates of the vertices for the image of triangle ABC with A at -1, 2, B at -2, 1, and C at -3, 3. Then graph triangle A prime, B prime, C prime given the composition rule xy such that 2x plus 1, 2x minus 3. And if you'll notice, we're multiplying something with the x, so that implies a dilation. And then we're adding or subtracting something with the x, which implies some sort of translation. So let's see what happens. We have A, B, and C. We're not going to have to make two complete moves. We're going to make 2 moves in one operation. So this is -1, 2, -2, 1, and C is -3, 3. Graphing those points, we have A at -1, 2, B at -2, 1, and C at -3, 3. So we have what looks to me like an isosceles triangle going here. Connect the vertices. And that's our pre-image. Now we're going to use the rule. So we take this rule right here. So we take A and it becomes A prime. We start with the first coordinate, 2 times x, which is -1, plus 1, comma, 2, the rule says, times, this is supposed to be a y, which is 2, minus 3 on this one. So that gives us A prime at 2 times -1 is -2. -2 plus 1 is -1. 2 times 2 is 4. 4 minus 3 is +1. So our new point is at -1, 1. For B prime, using the same rule, we start with 2 times x, which this time is -2, and then plus 1, comma, 2 times y, which is 1 minus 3. That gives us B prime. 2 times -2 is -4. -4 plus 1 is -3, comma. 2 times 1 is 2, minus 3 is -1. So we get B prime at -3, -1. And then C and C prime using this rule. 2 times x, which this time is -3, plus 1, comma, 2 times y, which is 3, minus 3. This gives us C prime. 2 times -3 is -6. -6 plus 1 is -5. 2 times 3 is 6. 6 minus 3 is 3. And so now we take these points here and see what sort of composition transformation we ended up with. Start at the origin for A prime, -1, 1. -1, up 1. This is A prime. B prime, -3, -1. To the left 3, down 1. So here's B prime. starting at the origin, -5, 1, 2, 3, 4, 5, up 3, 1, 2, 3, C prime. Connect the point, the vertices for this triangle. It's maintained its shape, but it is larger. So there's been some sort of enlargement here, but there's also been a slide or translation. It has slid out of place. It all came from this rule right here. Example 7. Find the coordinates for the vertices of triangle F prime, G prime, H prime, given that the vertices of triangle FGH are at F4, -8, G0, 12, and H6, -4. Using the composition rule, XY such that -0.25 Y, 0.25 X. Notice they've moved the X and the Y into different locations. There's a negative, which implies some sort of either part of a rotation or it could be part of a reflection. Doesn't seem to be any kind of translation though. So let's see what happens. They just want us to find the ordered pairs. So we start with F, 4, -8. So we apply the rule that we have. We get F prime. This is -0.25 Y times Y, and Y is -8, comma, 0.25 times X, which over here is 4. So we get F prime -0.25 times -8, of course that's going to be a positive, and we get +2. 0.25 times 4 is like saying 1/4 of 4, which is 1. So we get F prime at 2, 1. G at 0, 12. Applying the same rule. G prime, we have -0.25 times Y, which is 12, comma, 0.25 times X, which is 0. So G prime, 1/4 of 12, 25% of 12 or 1/4 of 12, that would be 3. And since negative times positive is negative, we have -3. Comma, and then 0 times anything is 0. So we get -3, 0 there. And then H was 6, -4. Applying this composition rule, we get H prime. Plugging in those values, we start with -0.25 times Y, which is -4, comma, 0.25 times X, which is 6. So H prime, 1/4 or 1/4 of -4 would be -1, and 0.25 times 6, that's 1/4 of 6. And so you would get 1.5 positive. These are the 3 new image points for when these 3 original image points in the triangle have been transformed using this composition rule. And finally, example 8. Find the coordinates of the vertices for the image of triangle XYZ with X at -2, -3, Y at -4, 1, and Z at -6, 0. Then graph triangle X prime, Y prime, Z prime, given the composition rule XY such that -0.5X, comma, -2Y plus 1. So this is going to be a sort of a strange one because you've mixed up X and Y coordinates. There may be a stretching or a shrinking of the figure. Let's see what happens. X is at -2, -3. Skip some space. Y is at -4, 1. And Z is at -6, 0. So graphing these on our coordinate system, X is at -2, -3, right here. Y is at -4, +1. And z is at -6, 0. Take a straight edge and draw your triangle. Looks like some sort of, it's not a right triangle, but it's a little bit bigger than a 90-degree angle at angle Y. So yeah, that triangle. Now let's apply the composition. X prime, here's our x and y coordinates. Here we go. -0.5 times x, which is -2, comma, -2 times y, which is -3, plus 1. This gives us x prime. 0.5 is the same as half. Half of 2 is 1, and negative times negative is positive, so we get +1. -2 times -3 is +6. 6 plus 1 is 7. So 1, 7 is our new location for x prime. Now for y prime, applying the same rule, we have -0.5 times x, which is -4, comma, -2 times y, which is 1, plus 1. And we get y prime at half of 4 is 2. Negative times negative is positive, so we get +2. -2 times 1 is -2. -2 plus 1 is -1. So we get 2, -1. For z prime, applying the same rule, we start with -0.5 times the x coordinate, -6, comma, -2 times the y coordinate, 0, plus 1. So z prime is at half of 6 is 3. Both of them are negative, so we get +3. -2 times 0 is 0. 0 plus 1 is 1, so we get 3, 1. So these are the 3 points we need to graph. Starting at the origin for x prime, 1 to the right, up 7. 1, 2, 3, 4, 5, 6, 7. There's x prime. Y prime is at 2, -1. To the right, 2, down 1. There's y prime. And z prime at 3, 1. There's z prime. Take your straight edge and connect the vertices, and as you can see, this triangle has been stretched. It has been flipped or reflected, and it looks like it's been translated a little bit too.